Good morning, everyone. So, in this series, let us discuss nested learning in simple terms. Nested learning, this is a latest paper just a month or so back, and the paper name is Nested Learning The Illusion of Deep Learning Architecture. So, this is published in Annual Conference on Neural Information Processing, and these are the four authors. They are all from Google Research. Now let us understand what it is and how it differs from deep learning and other kind of learning that we have been studying and we have been experimenting on. They can be associative memory, backpropagation, recurrent learning, momentum based learning. We have a lot of them in this paper. The authors have described how each of these and more can be written in form of nested learning, multi-step problem, right? So in layman terms, we are going to express higher layers in the form of lower layers in the form of lower layers, right? I'll explain this as we come to know. So let's first describe how we can express nested learning. So let us first see the basic definitions in which we are going to write nested learning. So for that, let us understand how we will be writing gradient descent. We all know what gradient descent is, right? It is the gradient that we are going to add to the weight term for multiplied with the learning rates, and say wt plus 1 is the weight at time step t. Then it can be written as wt minus eta t gradient at wt. L, the function that we all know what L can take the values. We'll discuss it in a separate presentation, and in brief I'll be explaining what L can be at the end of these slides. Now the author have written an equivalent definition of gradient descent as wt plus 1. This is the second one, is the one that we would be more frequently using in this paper. This is around 52 pages paper, and we are covering it in few slides to know what the gist is all about, right? So there are other parts of this paper that I would be discussing separately. Wt plus 1 is equal to augment W. So here we are going to take the dot product and uh, and W and plus 1 by 2 eta t norm of W minus WT whole square. So these two are equivalent and we would be using them interchangeably. Both we will be using, and some we would be using with even more refinements using some lemmas. So we'll see at the end. Associated memory. So for each key there is a value. So what is an associated memory like? So you are going to be given the keys. Say for example, in a neural network, somebody says a key value, say a place called say Taj Mahal. So associated with it is a value, a story that is there in the memory and in the learning process, that we have been using pre-training on it. We have given pre-training on it. Pre-training itself can be considered as the ground level of the nested learning, and the first level of the nested learning. So why we are doing all this? First of all, we have a pre-trained data, then we have a context, like I'm explaining to you with reference to associated memory. We have a key value pair, but in this the keys can be not just the words, it can be phrases, it can be gradients themselves, it can be other memory locations themselves, and the value that is associated from it, from the network, is what we would be interested in, right? What values are triggered when this key is entered, and the key can be more than tokens, as I just explained. So what it is in pretext, we have given this, but the problem is what happens is why we need nested learning. When we get a context, after some time this context is lost somewhere in the computations, right? I'll explain that also. Like we are on the fourth level uh, of the gradient descent or deep learning feed forward networks, and here the first context is lost. and we are at the 5th level. Then we go to 7th level, then the 4th context gets lost. So how do we keep track of all those learnings that we learned in between? So here associated memory plays a part, but how do we retract it, right? How do we keep track of it? So let's see how we would be doing it in nested learning process. So keys is now key at time t is wkxt. Xt is the input at time t. wvxt is the value. Wv is the corresponding memory associated with the value. Qt is wqxt. Here again, this is the query, and wq is the memory associated with query. Now mt is equal to mt minus 1 vt kt. V is again the value, k is the key. So this is how it is mapping. And what is the y here? It is mt qt. That is very much evident from associated memory notes. You can read that, right? So it is clear here. Yt is equal to mt qt, right? So now what is the surprise in learning? Let's just get into the surprise of learning. If we present xt plus 1, right, input at t plus 1, then wt plus 1, if we use the same formula, this would get the surprise in the learning. This is amounts to the surprise in the learning. So now nested optimization processes. For that, they have defined the authors in the reference 1. All of these are taken from reference number 1. Please refer to them. This is taken as it is. For any component of A which can be parametric component, example learnable weights or momentum terms and gradient descent with the momentum, or non-parametric component, we define its frequency FA as number of updates per unit time, right? So now what is nested system? May look a bit complex, but it is very much understandable if you understood the gradient descent definition I gave you. And I gave you means it is given in the paper only. So the gradient descent explanation and the key value associative memory. So these are the two things that are important. I have taken those two important things from the paper because these are too generalized to nested systems. And that was the reason why I explained those two terms of associated memory gradient descent and the updated gradient descent, in which they have used this term 1 by 2 eta t phi ik theta ik norm L2 norm. So now, an ordered nested system is a system with k ordered levels such that at each level k in the range 1 to k consists of optimization problems. So, each level k has an optimization problem. Lik is the optimization objective of the ith problem. Cik is the context, the data that is to be optimized on, and theta I is the feasible set of parameters, and each parameter is optimized using gradient descent. This is just the same as what I have presented above, but the only thing is they have added layers in it. That is, at each layer we have a subscript I and k, and this is the optimization objective at ith problem, right? So there are two parameters k for the level, and ith problem is that ci is its context, theta is the feasible regions. So this is what the optimization problem looks like, right? This is a nested system of k levels. Now next is nested system of associated memories. So what is it? It is NSAM. So what is the difference between this and that? Both looking complex, but the thing is that is related to the gradient descent definition that I gave you. This one is related to the associated memory definition that I gave to you. I gave you two definitions, right? The gradient distance, that we have done the simplification of the nested systems from that, and here it is associated systems. So here, what is it? A nested system is an nested system of associated memories is a system of k ordered levels 1 to k consisting of optimization problems Lik, Cik, Theta k, I equal to 1 to nk. So for each level, we have nk optimization problems, right? For each level, we have nk optimization problems where Ci is again same as last time, the context, and kj, vj. So what is the difference here? There we were explicitly doing, here we are using in terms of key and vectors. So this is key at ith, at the ith level, ith system, and k is the level, right? Each level has 1 to nk optimization problem, context, and parameters, right? Each level has 1 to nk optimization problems, context, and thetas. That is the parameters. And the upgrade rule is given like this: theta of I at t plus 1 time, here time also comes at the kth level, is equal to this definition that was there. I described it to you before also. It is here. If you see this definition, the second one, 1 by eta t, norm of w minus wt whole square, and there is the dot product. So here we are going to see theta phi I k t plus 1 I. Here there is the keys, and they are with the phi i's, and they are here in the L optimization function. We have theta it k kt plus 1 vt plus 1. So keys values are here so that the optimization can just see what the typical optimization problems are like. The L can take values like dot product or the loss function. There are various values. So here key and value, if it was w, we generally take it as a norm w minus y whole square, something like this we take, or we take the dot products. But here it is key value. So key into the parameter is equal to a value, right? So it can be minimized here also. This term is same as just what I have shown it to you. So this is NSAM, nested system of associated memories. Now continuum memory system. So here MLP at a frequency Fi is equal to MLT pre-trained at the 0th level. How do we initialize it? At the 0th level, it is equal to just the pre-trained. So what is a pre-trained? It is same as what we have defined now, but what is written and what is explained in the paper is that pre-trained is itself a instance of this learning. But at this pre-trained level, you learn something which is difficult to change at later level. Later level we get the context, but context is lost. We lose the context and we are just related to the pre-trained values and the new context. So if we use this, the paper argues that it will be as shown in the experiment results. It is coming out to be well on different data sets and GenAI problems. So YT is equal to MLP. It is like a nested thing. At Fk is actually a function of MLP at Fk minus 1 and up to so on. And at the 0th instance, it is the pre-trained MLP, where parameters at Lth block are updated at every step. This is continuum memory system. Now deep self-referential titans. I'll discuss about the titans in separate way. So you'll just understand like the associative memory. The key at the time t, it is here, is mk t minus 1 at xt. Values mv t minus 1 and xt. Query mtq minus mt minus 1. It is a memory of, we have just seen the update rules Memory can be described as in weights or parameters, or in general we can write it in M as a memory term. And minimizing, these are the optimization problem. The square here denotes it can take any value from key value query or the parameters, right? And it is updated with an optimization algorithm. Minimize, again with the optimization problem, KTVT, because this is the associative memory. Are we doing it right? The key values, key into parameters is actually giving us the right values. This is what the optimization is all about. YT is equal to memory at QT. So we also compute YT here. YT is the output when the query is being triggered at this model. YT is the output when query is triggered at this memory at time t, right? So, self-modifying deep associative memory where models generate their own value. This is again a variant. Here, the second step changes. Here we define V hat of each of the key value query and parameters as memory at t minus 1 of Vt, and this is defined for each of key value query and parameters. And the optimization is same. We are doing the same thing, optimizing M at key kt V hat of t. Here there was Vt, here it is V hat of t. So these are self-modifying deep associative memory where models generate their own values. These are the models that have generated their own values. So this I have already discussed. What is the optimization function? Can be L2 regression loss, it can be dot products and more, but the paper have limited itself to this only. There are papers in which there are different kind of L that have been considered. So I'll discuss that as it comes. Now they have just modified the definitions using Sherman-Morrison's lemma. It's stated here. This is the lemma. So if we use this in the expansion of the gradient descent that I have explained in the first slide, you will get this. Wt plus 1 is equal to Wt and this expansion. So it is just writing in different form, and we get, if we use this lemma, Sherman-Morrison lemma, we will be getting the Hope neural network module in this format using the lemma that we expanded gradient descent as. This would be the new expansion of it. So it's just a different representation and a clear representation of the lemma, so we don't have to do other things. So once again, this is the paper, Nested Learning, the Illusion of Deep Learning Architectures. It was published in Neural Information Processing. It is a great paper to read, but 50 pages is quite time consuming. So here I am presenting to you the shortened version and the key points of it. They are in the coming series. I will be discussing with you more on associative learning, how backpropagation can be written as associative learning. If it can be written as associative learning, our formulas of the key values and all those things can be used, and we can apply the algorithm here, the Hope algorithm that has been explained here, right? Thank you. Subscribe for updates.